Okay, so we are back with lecture 9 of time series analysis. Now we're going to see some methods based on extreme value theory, empirical estimation, and other things related to value at risk. So we're going to call xn to the sample maximum of a loss variable. Extreme value theory is concerned with the limited distribution of xn after some proper scaling and centering as n goes to infinity. What does this mean? For independent samples, the limiting distribution of the normalized maximum, given in this way, is given in this way. So here we call nothing. We just use this e value. I think it's epsilon. Yeah, could be epsilon. So it's exponential of minus 1 plus this to this power, if it's not 0, and if it's 0, well, exponential of minus the exponential of minus x. So here, if epsilon is smaller than 0, we have x has to be between minus infinity and minus 1 divided by e, and it's got to be greater than minus 1 divided by if e greater than 0 over the subscript asterisk signifies the normalized maximum. This parameter is referred to as shape parameter, and it governs the tail behavior of the limiting distribution. In order to take another Greek letter out of the equation, we're going to call alpha to 1 divided by e. I will call that tail index of the distribution. So, there are three types of limited distribution given by Nedenko, 1943. And for type 1, if e equals 0, we have the Campbell family, whose cumulative distribution function is given by exponential of minus exponential of minus x for x between minus 1 and 1. Type 2, if e is greater than 0, we have the Frechet family, cumulative distribution function defined in this way. And if e is more than 0, we have the Weibull family, cumulative distribution function given in this way. So, probability density functions of extreme value distributions for normalized maximum are given in this way. The solid line is Campbell distribution, dotted line is Weibull distribution, and dashed line is Frechet distribution with these values over here. So they're pretty different. Now, extreme value theory has two important implications. The first one being that the tail behavior of the cumulative distribution function determines the limited distribution of the normalized maximum, and the sequence of means and the sequence of standard deviation depend on the cumulative distribution function. You can go to McNeil, Free, and Embridges for more info on that. And for the third implication, the tail index does not depend on the time interval, which is important. I mean, the tail index is invariant under time aggregation, which is really handy in the calculation of value at risk. For empirical estimation and demonstration, we have three methods: block maximum method, maximum likelihood method, and the non-parametric approach, which is the Hill or Pickant estimator for the shape parameter E. So here we have the Hill estimator for the daily log returns of IBM stocks with the corresponding standard errors. So here look that actually these estimators kind of follow the curves pretty well. Estimator for positive returns, estimators for negative returns. So for maximum likelihood estimates, seeing value distribution, we're giving this in percentages. Maximal positive returns are given in this way. Maximum negative returns are given in this way, from 1 to 2 months. This is the shape parameter, scale, and location. Okay, so these are residual analysis of fitting GEV distribution to the negative IBM daily log returns in percentages. Here the subperiod used is 21 days. So this looks a bit chaotic when you before you order it, right? And then when ordered it becomes much nicer. So the real question here is how we apply this to risk measures. So for a given small upper tail probability P, value at risk of a financial position with loss variable x sub t is given in this way, where n is the length of subperiods. This logarithm makes you think of some sort of an inverse function, right? Well, there is something kind of over there. So we can summarize the approach of applying the traditional extreme value theory to value at risk calculation in this way. Firstly, we select the length of the subperiod n and obtain subperiod maxima, a value of x sub ni, where g is basically sample size divided by the length of periods, by the number of periods, sorry. Second one, obtain the maximum likelihood estimates for mean, standard deviation, and shape value. Third, we check the adequacy of the fitted extreme value model. Now we'll see this in the next section. And fourth, if the extreme value model is adequate, we apply equation 16. Where are you, equation 16? Equation 16. To calculate value at risk. Sorry, this is an erratum. This equation 17. It's this equation here. Now, under extreme value theory, multi-period value at risk is calculated in this way. Value at risk with an n period of lag is set number to the power of the shape value times the value at risk. For an example, let's take the daily log returns in percentage of IBM stock. From the previous calculation, we have estimates for alpha, beta, and the shape value for n equal 21. And so for the left tail probability p equals 0.005, the corresponding value at risk is given by the equation 17, and we have 1.8902. So for the negative daily log returns of the stock, the upper 1% quantile is 1.8902%. Consequently, value at risk is given this way. That's $18,000, roughly $19,000. If the probability is 0.01 instead, the corresponding value at risk is a bit bigger. So if we choose n equal 42, then estimates vary a bit, the shape factor changes a little bit, then the upper 1% quantile of the loss variable based on the extreme value distribution is given in this way, and so the corresponding one-day horizon is this percentage of our initial $1 million, which is roughly 35.5k. If probability is 0.05, the corresponding value at risk is a bit more than 17,000k instead. So in this particular case, the choice of n equal to 21 gives higher VAR values. Now, the reason I have used the same example here is so we can compare different applications, different models, and what results they bring. So for risk metrics, value at risk is this number over here. For Gaussian GART11 model is this number over here. For GART11 model with a standardized t-student distribution with these degrees of freedom is this value over here. Empirical quantales gives this. Quant regression gives this. Traditional extreme value theory gives this. So big differences here really. If the probability is 1% instead, the values at risk are like this. And so this kind of makes us believe that probably the last three in both cases are actually the worst approaches to value at risk. Regarding our expectations, however, it's not exactly like that. More like in financial terms, these three are the most conservative estimates. So it makes us ready for bigger actual losses, considering that the value at risk is a bit bigger. So if we accept the same amount of value at risk, we are ready for. I mean, a bigger loss is not such a shock as it would be in other less conservative models. Now we're going to see an interesting two-dimensional framework where this is called peaks over thresholds. The basic theory of POT approach is to consider conditional distribution of x equal to y plus v, given that x is greater than v for the limiting distribution of the maximum given by equation 13. So conditional distribution of x being bounded by e times v, e plus v, given x is greater than v, is exactly this one. And so we can use the cumulative distribution function and this approximation. This is true for smaller z numbers. And some algebraic transformation that I'm going to omit for everyone's sake. And we have this nice equation here. So this condition probability is basically 1 minus this exponential that only depends on the mean, a parameter eta, shape value, and standard deviation, condition to this. Okay, that's pretty manageable already. Now for generalized Pareto distribution, in the case where the shape factor is 0, we can take it as the limit where the shape factor tends to 0. And so if we do that, this equation here becomes this equation here, which is much more manageable. The probability distribution with this cumulative distribution function, where this is exactly the limit and this is the equation for the rest. This is called a generalized Pareto distribution. For generalized Pareto distribution, we suppose that the excess distribution of x given a threshold v sub 0 is a generalized Pareto distribution with the shape parameter e and scale parameter phi, psi of v sub 0. Then for an arbitrary threshold, I mean v is greater than v sub 0, the excess distribution over the threshold is also a generalized Pareto distribution with the same shape parameter and the scale parameter, this psi of v is psi of v sub 0 plus the shape factor times v minus v sub 0. So it's kind of like this psi of v minus psi of v sub 0 is actually a multiple of v minus v sub 0. which is great. This is really easy to operate with. Now, related to this, we're going to define the mean excess function in this way, where n sub v is the number of returns that exceed v, and x sub ty are the corresponding returns. So we're going to take, so this is the mean of the exceeding returns. That's why it's called mean excess function. For an alternative parameterization, we use psi sub v as alpha plus the shape factor times v minus beta, and the parameter of the generalized Pareto distribution becomes this. Now for estimation, for a given high threshold, we can use generalized Pareto distribution to obtain parameter estimates. For our long position of 1 million of IBM stock, we have this variable risk and this expected shortfall. For the first trading day of 2011, when the threshold of 1% is used, if the threshold is 1.2%, this is the new value at risk, and this is the new expected shortfall. Look like the expected shortfall is a bit smaller, but the value at risk is a bit bigger. And for a threshold of 0.8%, we have this value at risk and we have this expected shortfall. Now for the maximum likelihood estimates of the generalized Pareto distribution, we have this table of estimates, okay? Now, these are diagnostic plots for generalized Pareto distribution to fit the daily negative log returns of IBM stock. We can see that they fit pretty well. Now, I'm going to see some techniques for credit risk measurement. First of all is long-term credit rating. It goes from high to low. Standard & Poor's does it like this. Moody's does it like this. And Fitch does it the same way as Standard & Poor's does. These are the three main qualification agencies. Now, for a credit quality over time, I mean, transition rating, Standard & Poor's uses this 1 year transition matrix, which these are the probabilities of going from this state to this state in percentage. So if you sum all this, they should go somewhere close to 100%. Okay, maybe I went a bit optimistic. 96.56, 97. Yeah, okay. Considering cut errors and everything, this still sounds roughly 100%. So yeah, this is basically a transition matrix. Now there is an R package called Credit Metrics. It's pretty interesting. It includes JP Morgan. It includes other sponsors. You can use it for credit risk here. Now there is another score. It's mainly used in the US. It's called Alban Z score, which is 3.3 times the earnings before interest and taxes divided by total assets, plus the sales divided by total assets, plus 0.6 market value of equity divided by book value of debt, plus 1.4 multiplied by this, plus 1.2 multiplied by this. And there's another one, which used to be KMV Corporation's credit risk model, but it has merged with Moody's. So they use this classification as well. Now, credit metrics addresses the following questions. How much will I lose in my loans and loan portfolios next year for a given confidence level. So from the assessment of market risk, the current market value and its volatility of financial position play an important role in value at risk calculation, really. Now, the application of VAR methodology to non-triable loans encounters some immediate problems. First, the current market value of the loan is not directly observable. The reason why being that most loans are not traded. Most loans are just there. Second one, there is no time series data available to estimate the volatility. And so we have to do things to what's the word, to jump over these difficulties. So in order to do that, we can make use of available data on borrowers' credit ratings, and so we can build some proper estimates. The probability that the rating will change over the next year with the transition matrix, recovery rates on defaulted loans, and credit spreads and yields in the bond or loan market. So we basically would use this data to build proper estimates and be able to work with as much precision as we can. For an example, let's say we have a loan of 100 million, 6% annual interest, and the borrower is rated BBB. The numerical numbers used in this example are for chapter 6 of the reference book cited above. So 1 year transaction probabilities for BBB rated borrower are like this, so most likely we will stay BBB. So valuation rating change will affect the required credit risk spreads or premiums on the loan's remaining cash flows, and so the implied market value of the loan. So a downgrade means the credit spread premium rises and mean that the present value of the loan should fall. And an upgrade means that the present value of our loan should rise. So after 1 year and a credit rating change, the value is given like this. But here, R1I are the risk-free rates on zero coupon US Treasury bond, the US Treasury bonds expected to exist 1 year into the future, and SOY is the annual credit spread on loans for a particular rated class of 1 year, 2 year, 3 year, and 4 year maturities, derived, of course, from observed spreads in the corporate bond market over treasuries. Okay, this was a very long sentence. So the value of our portfolio, the value of our loan, if we suppose that the borrower gets upgraded from BBB to A, then the value of our loan is given in this way. So it's roughly $800. So the value of the loan at the end of year 1 under different rating changes is given in this way. So for our value at risk, a new loan value plus coupon, this is given in $1 million, by the way. This is given in $1 million. I was thinking $100 isn't a very small amount. It is indeed. So this is actually measured in $1 million. So yeah, after getting our nice coupons and everything, then the new loan value is given like this. If our borrower goes from BBB to A, probability weighted value is like this. Difference of value from the mean is, well, it's roughly 1.5% bigger. And probability weighted is in this way. From the table, we know that the mean value of the loan is $107.09 million. This is the sum of the fourth column. So the difference of the value here is 8.9477. Consequently, the standard deviation is the square root of this. This is the variance actually. So the standard deviation is $3 million. If normal distribution of the loan value is used, we assume that this is normally distributed. At 500%, we have value at risk of $4.83 million and $6.87 million at 1%. If actual distribution is used, we have this value at risk at 6.77%, this value at risk at 1.47%, and this value at risk at 1.7%. Look that the 1% number is obtained as interpolation. And this was the last example. This is as far as theory goes. Value at risk is actually quite a complicated task to do because there are so many different coefficients and variables and everything to follow. I just recommend that you take it very slow and check very carefully on what each coefficient means. So when you operate with it on R, you can just know where to take it with and where to take it from, and operate with it directly instead of having to go here and there to calculate it. I mean, if there is a direct form to calculate it, I suggest that you use that as often as you can, because otherwise there is a lot of small details hidden here, and so it can make a bit of an additional difficulty if you don't take the straight formula in count. And so that was it for me. This is as far as lectures goes. I really hope you're learning as much as you can. I hope you're having a good time attending these lectures. And well, I'll see you in the next session. Please stay safe, please stay hydrated, and that was MMA 702 for me. Thank you very much.